Hello, everyone. Welcome to AAS Publishing, and we are back in another of the author series. And I am delighted today to have Hannah Wakeford, who's going to talk to us a little bit about WASP 39b. Hi, Hannah.
Hi, everyone. Hi, Frank. Thanks for having me on.
Sure. Where are you at, by the way?
Right now, I am at home. Welcome to my house.
Okay, where's home?
In Bristol, and I'm a lecturer at the University of Bristol in the School of Physics.
Awesome. I was at Bristol last year because our publisher, IOP, is out in Bristol.
Yes, they are.
I visited Bristol for the first time last year. You have some lovely countryside around there.
Yeah, it's a beautiful city. Very empty at the moment, but beautiful.
Yeah, and I even went and saw, oh shoot, now I'm spacing, planet person, Carol Herschel's. I went and saw the Herschel stuff. Very cool. If you ever get a chance to go to Bristol and you want to see where the Carolyn and company did their observations in Bristol, it's very cool to see. So,
it's a very historic city.
Absolutely. Loved it. Okay, so we are going to walk through one of Hannah's recent papers, and here we go. So I'm going to bring this up. I'm going to do a screen share, and we will walk through the complete transmission spectrum of WASP 39b with a precise water constraint. And Hannah, take it away.
Yeah, so this paper is looking at a very specific planet. This is a planet called WASP 39b. It was discovered by the WASP survey, and it is a Saturn mass exoplanet. So it is about 89 times Earth's mass, but instead of being like Saturn, which is only about 9 times the size of Earth, it's actually 14 times the size of Earth. So it's a really puffy planet, very low density. So when we talk about Saturn being quite low density, this is much, much lower. So it's a very, very puffy planet. And what we did here is we used the Hubble Space Telescope to try and observe its atmosphere, understand what its atmosphere is made of. And we do that using a technique called transmission spectroscopy. So we're looking at the planet as it passes in front of its star, and the starlight shining through that atmosphere is being absorbed by the atmosphere. And then we get that light out the other side, and we get a wavelength dependent imprint, so a spectrum of the absorption signatures of the planet's atmosphere. So we use this over a large wavelength range. So with the Hubble Space Telescope, we can go from the optical to the near infrared. Mm-hmm. And we also use the Spitzer Space Telescope to get 2 observations in photometry out in 3 microns and 4 microns. And that gives us a nice big picture of the absorption signatures in the atmosphere of this planet.
Cool. What's the distance?
To WASP 39?
The distance from the host star to the planet.
So WASP 39 is on a roughly kind of, I think it's a 5-day orbit. So it's very, very close to its star. So we're talking something 8 times closer than Mercury is to the sun. These are hot planets, and they are also tidally locked. So they have a permanent day side and a permanent night side. Okay. So what we're observing here when we're looking at the planet passing in front of the star is actually this terminator region, this limb around the planet itself. Okay. So that's the transition from the day side to the night side of the planet. And if you go down to figure 1, you'll be able to see what our observations actually look like. Now, when you think of the Hubble Space Telescope and taking images and observations, you normally think of these beautiful nebulae and these amazing pictures of galaxies. But when it comes to exoplanets, when it comes to stars, what we actually get is this pinprick of light. We get this point source. So that is just showing you what the star, WASP 39, looks like. And in the bottom there, you're seeing the spectrum of the star, so the light of the star spread out across the detector so that we can look at the wavelength dependence of that. And what you're also seeing here is that it's kind of in a box shape. And that's because what we're doing is we're scanning the telescope. We're physically moving the Hubble Space Telescope during this observation to spread the light out across the pixels. So it's a very, very strange observation. We're constantly nodding the Hubble Space Telescope as it's orbiting around and taking pictures.
Do I understand this figure right then, that it takes roughly about 100 seconds to transit?
So this is actually 100 seconds for just one single observation. And if you go to figure 2, you'll see how many observations we got of this planet as it passed in front of its star. And one of the interesting things that you're seeing here, you're seeing 3 different observations that we looked at in detail in this paper. And you're seeing the ingress, so the dots as it goes down, as it starts to dip, that's the planet as it starts to pass in front of the star. So it's not quite all covering yet. So you only get the ingress there. And you're also seeing these gaps in the observations. And that's because the Hubble Space Telescope is in orbit around the Earth. And every 45 minutes, the Earth actually blocks our view of the star. So we get chunks of data. And that's what you're seeing here across 2 different instrument modes there.
Got it.
And then if you go to the next one, we show it in a slightly different way. This is showing you a pixel map of those observations. So what you're seeing in the y-axis is the exposure number. So you saw up there that there was lots of different data points. Those are our exposures, each of them about 150 seconds long.
Okay.
And each of those rows is then the wavelength. So that's the spectrum of the star itself. And you can see in that top panel, just that kind of slightly darker band. This is the spectrum of the star. And then the planet passes in front of it and it blocks some of that light. So it makes it dimmer.
Oh, that's pretty cool. Yes.
And that's what you're seeing in that middle one, is that kind of normalized dimming of the star itself.
Very cool.
And then that bottom panel with that kind of very, random noise pixel map is showing you what the results are like. So showing you how well we're able to analyze these data. It's showing you that because you're not seeing any patterns in that noise, we've managed to take out all of the systematics, all of the things that will be causing changes or time consistent things based on the telescope. So we've been able to take out all of the systematics that we understand and some of the noise profiles, and we've got really good observations left behind.
Just for reference, what's the spectral type of the host star?
The spectral type of this one, I believe, is a G0 star.
Okay.
Yeah, so it's fairly common.
Yeah.
And then if you look at the next one, what you're going to see is that this is the measurement that we actually got of the planetary atmosphere. And what you're seeing here is a number of different observations combined together, really importantly. And what you've got there is a absorption feature from water vapor in the planet's atmosphere. Now, when we look at a transmission spectrum, it's kind of flipped from what you would normally expect from an absorption signature. So if you're used to looking at absorption signatures from gases or things in labs or a spectra of stars, you normally see it as a dip.
Right.
Now, because we're observing it in the planet's reference frame, as the planet passes in front of the star, if the atmosphere is absorbing the light, it appears bigger, so it blocks out more light. So that's what you're seeing here. It's kind of a flip of those spectral features because the absorption makes the planet appear bigger, and therefore it goes up in size.
Right.
And then down again when you're outside of that. So what you're seeing here are the very characteristic peaks of water absorption, which you would also see if you measured the Earth's atmosphere.
Very cool.
Now, what we need to do next for this, so we've done our measurement, and we've taken 5-6 pages to get to the point where we try and understand it. We've had other colleagues and collaborators doing the analysis as well. Can we get the same answer? Yes, we can. That's great. But now we need to understand it. We want to kind of put that into context. What does that mean? And this is really the token figure of the paper. This is showing you the full transmission spectrum from that optical to the infrared, like I described at the beginning, with models that have been fit to the data. So we use this retrieval framework, which a retrieval is a way of fitting different parameters to a planet using forward models. So models that are generated based on all of the different kind of parameter phase space that you're looking at. And here we're looking at all of the different chemistry in the atmosphere, the temperature of the atmosphere, the size of the planet, the ratio of carbon to oxygen in the atmosphere, and a huge number of different things combined together to try and understand what we're seeing here. And what you can see is that, it's nicely labeled there for you, is that we're measuring sodium, potassium, water, and potentially some CO2 in the atmosphere of this planet. And that water absorption feature that you can see there, those 3 distinct bumps in that near infrared region, is one of the most precise measurements that we've got of water vapor in the atmosphere of exoplanets so far, which I think is really exciting.
What's the relative abundance of that water?
So that's one of the really important things that we were trying to find out from this. Yeah. And this paper kind of threw a spanner in the works because of that. Okay. What we were trying to do was trying to work out how much water vapor there is. And what we found was that there's around 150 times the amount of water vapor in this atmosphere compared to solar. So compared to our sun, there is 150 times the amount of this heavy oxygen bearing species, water. And that's really surprising because, like I said, it's a Saturn mass planet. Now, Saturn in our solar system only has about 10 times the amount of water as the sun, so 10 times solar. Right. And Jupiter's 4 times solar. So this is a lot higher. And if you go to one of the figures a bit later, you'll be able to see that in context. Okay. So I think it's...
Where do you want to go?
Down a bit more.
I
think it's one of the last figures in the paper, and then we'll pop back and discuss some of the reasons why we're able to make these measurements.
13?
So if you, no, I think it's 15 or so.
Okay, farther down. 14.
There we go, this one, 14.
14. Okay.
There we go.
Follow that up. All right.
So what this is showing you is that water abundance that we measured in terms of overall atmospheric metallicity. So as astronomers, we all know that we use anything greater than hydrogen, helium means it's a metal. So this is using water as a proxy for the abundance of metals in the atmosphere.
Okay.
So using that oxygen essentially. And what this is showing you is that compared to our solar system, which you can see there, where as you decrease the mass of the giant planet in our solar system, yes, you increase the metallicity of the atmosphere. You increase the amount of heavy metals it has in its atmosphere. And on there, you're also seeing a number of data points from other exoplanets. But this WASP-39 measurement that we made here is just so far off that line that it kind of puts into question the formation scenarios. So this likely suggests that WASP-39b itself, the planet, formed very far out in its planet's disk, which allowed it to acquire lots and lots of ices, lots and lots of heavy materials in its atmosphere, which then contribute to the overall abundance of these materials. And then it would have had to have migrated in to where it is today. So it gives us a little bit of a clue about how these planets formed and what they had to have been formed of, so that they get these amounts of material that we're just measuring.
Wild. Okay.
It's one of the exciting things about exoplanet studies is we're just trying to put our solar system in context. And one of the ways we're doing that is by comparing these giant planets we're looking at to our solar system giants and trying to understand fundamentally how did they form and evolve, and can we make a comparison between those? And we're really starting to dig into that now with exoplanets.
Yep.
Okay. But I want to just head back to 13, just to kind of finish up. And talk about this figure, because I think one of the really important things that we showed with this paper was just how vital all these different wavelengths are when you combine them together. So what you're seeing here is us looking at the data that we got of this planetary atmosphere and breaking it up into chunks. If we had just measured the infrared part of the atmosphere, what would we have learned? If we had measured the whole of the atmosphere from the optical to the infrared, what additional things can we learn from that?
Okay.
And what you're seeing here in purple is the infrared portion that we measured and what we then can assume or predict based on those measurements alone. And you can see that the amount that's spread in the purple in the optical is very, very wide. We wouldn't have been able to learn a huge amount about this planet and what that means, because the optical is the most important thing that we're learning about, is how particles in the atmosphere scatter light. So without the optical data, if you go to the side, you'll see those histograms. They're showing you the critical things we want to understand about this planet. Now, those critical things are the temperature, the atmospheric metallicity, the ratio of carbon to oxygen, and these cloud parameters. So is it scattering light, so small particles in the atmosphere, or is it got large particles in the atmosphere scattering the light? And the difference between the purple and the green, where the purple is just using a very small amount of information and the green is using more information, really just highlights how vital observations with the Hubble Space Telescope are in the optical portion of the spectrum. And that's something that we really, really wanted to push with this. And I was really fought to keep this figure in here because I think it really, really highlights how important Hubble is going to be now and well into the future in understanding planetary atmospheres and kind of putting them into that context.
In JWST?
And James Webb's going to be amazing. So James Webb's going to be getting us all of that infrared data, but it can't get us this optical data. It can't get us this information that Hubble's getting us. And that's really the important thing, is widest wavelength coverage possible, measure as many things in the atmosphere as possible, and those histograms, those constraints that you can get, just get tighter and tighter, and we can really start to place these as an object that we can pick apart and understand its environment and its nature.
Nice, nice. Well, I'm glad you fought for those histograms. I think they're very nice. Those are informative.
Took me a long time to learn how to do those in IDL, but I have since learned Python, so I'm getting better.
Ah, okay.
But yeah, that is the WASP 39 paper.
Well, very nice. So let me ask, now that we, where do we go from here? Where does the community go from here, given what you've published on WASP 39b?
Yeah, so that's an important question. And we kind of hinted at it just now, talking about the James Webb Space Telescope. That's going to give us access to even more wavelengths. It's going to fill in all of that blank space where we just had model predictions. So we've predicted for this atmosphere that we're going to measure a very strong CO2 feature in the infrared at 4.5 microns. That's a prediction that we've made based on the observations that we've got with the Hubble Space Telescope. We need to show that that's real. If that's not, then that kind of throws into question what we've been measuring here and whether or not we're missing something in the models, or if we're missing something in the data, that it's not able to explain that very well. So the James Webb Space Telescope observations are going to be really important for this planet, for us to kind of pick apart both aspects of these types of studies. But another thing that is going to be really important is just expanding this to loads of different planets. One of the special things about WASP 39b is that it is a Saturn kind of mass world. There aren't actually that many exoplanets that are around Saturn's mass. Most of them are, you know, that we're able to look at. Roughly 10% of all of those 4,000 or so exoplanets, we can study their atmospheres. And out of that kind of small 10%, most of the ones that we're looking at right now are Jupiter-sized or bigger, massive planets, or Neptune-sized, because we now know from the Kepler mission that Neptune-sized worlds or smaller are the most abundant in our galaxy, which is fantastic. But these Saturn-sized worlds, there's not many of them. So why is that? What is it about them? We need to understand them a lot more. So we're trying to fill in that diagram. We're trying to pick apart those, you know, nearly 100 worlds maybe that we can study in detail and try and understand their atmospheres, so that we can really make those comparisons to our solar system.
Are there any ground-based programs on this, or do you definitely need to get above the atmosphere to get above the Earth's water content, for example?
Yeah, so for looking for water vapor, like we're doing here, you have to go above the Earth's atmosphere. That's just like looking through a cloud of water, quite literally, to look for water on another atmosphere. But for things like sodium or for helium, we can detect that from the ground. So there's been lots of amazing ground-based studies that are doing high dispersion spectroscopy, high resolution observations from the ground. The Hubble Space Telescope, these observations that we've got in this paper are very low resolution. So there's a lot of different complementary ways that we can measure this. The nice thing about space-based observations with Hubble is that they give us the absolute depth of the atmosphere. So they give us this baseline and they tell us how the absolute changes in the atmosphere are kind of reflected on that planet. But with the ground-based high resolution, you get a beautiful abundance, but you don't have an absolute depth. So you can't put it into context. So it's actually in the combination of these two methods, from ground and from space, that we're going to get the most information. It's just quite a difficult puzzle to unpick. And there's some people that are doing that a really great job with that.
Cool. Where should we be in 10 years? Looking at your ball.
Hopefully with an army of Hubbles in the...
An army of Hubbles, wow.
An army of Hubbles. No, I'm really hoping that we've got a really good understanding of James Webb Space Telescope. I would love it if Hubble's still kicking around and getting us observations. I would absolutely love that. We're still unpicking new instruments on the Hubble Space Telescope. One of my most recent studies was using another instrument on the Hubble Space Telescope for the first time. Like, it's been on there since 2009, but it's never been used. So we're still picking apart this amazing 30-year-old telescope. And I'm really excited to continue doing that and continue exploring these atmospheres. I'm hoping that with TESS and with other space-based and ground-based surveys looking for more planets, we'll have hundreds and hundreds of worlds that we can explore in detail.
Yeah. Awesome. All right, Hannah, I want to thank you so much for sharing your paper with us, your article with us, I should say. So folks in the know, feel free to contact Hannah via email. Of course, we will not be putting that in the description of YouTube, but Hannah is not hard to find if you want to find her and talk about exoplanets or other stuff. So that'll do on this one. I want to thank everyone. Thank you, Hannah, very much.
Thank you.
And let me do a stop share here, and we'll get one final shot of us, and we will stop. Bye-bye.
All right. Bye.